Okay, I trusted that you could still do those. Are we okay with slope fields? Or do you want me to go over an example?
Example.
So, what you're going to be given is called a differential. It's the derivative, right? So you're given a derivative. Whoop. Need a marker. Okay. To find the original function and graph it, you can use slope fields, but it doesn't give you the location up and down, because if you integrate this, you get a plus constant, right? So it doesn't give you the y value. Okay. So, but basically what this is just calculating a ton of slopes. All right. So if I pick that function, dy dx, it's going to give me, oops, sorry, I should do it this way, x, y. A point is going to give me a slope. Right. So if I choose 0, 0, 0 plus 0 is 0, right? So I can go to a grid and I can put a slope of 0 at 0, 0. And then I can go, okay, so, and then just, you're going to be given, right, 1.
It's kind of weird. You said 0, 0, and then Mr. Porter said 0, 0.
That is weird. Okay, so you can calculate a whole bunch of slopes, right? And on your slope field, what do we have? 1, 0, 0, 1. -1 and -1, right? And those don't have to be perfect. But then if we went to -1, 1, we'd get 0 again, right? And 1, -1 is 0. So these are all going to be 0, the diagonals. Okay. And then let's say we went to 1, -2, we're going to get -1 on this diagonal, right? So the key there would be to look for patterns. Okay. And then if I went to -2, you know, our slope's going to be -2. And the key here is to make these relative to each other. Just make this one steeper, because it's more negative slope. Okay, and then this would be 2. So just make it a touch steeper. Right. Okay. And then again, it's one steeper. You kind of see, oh, I went too far. We can't place the graph up and down precisely unless you're given an initial condition. Okay, so if you get a slope field and they ask you to graph the function, they might say, given y at 0 is 1. That's your point where the graph has to go through. And you're just going to follow the slope field. Sketch that graph through those slope fields. Okay. Make sense? So just follow the lines. It's like connect the dots, calculus style. Alright, so that's a slope field. Right? You can either be asked to draw one where they'll give you only like 6 points, or you'll be given, this is a popular multiple choice question. Here's a differential, pick the slope field. Right? Okay. So there you go. Okay. So that's graphically looking at the solution to a differential. You can also do it algebraically. Do you remember how to solve a differential from last year?
Is that where you separate the dx and dy's?
Yeah, it's called separation of variables.
Oh,
vaguely. So,
When you integrate it,
Yeah, so you have to split the x's and the y's up so you can calculate the.
so this is like
integrals.
implicit differentiation just with integrals?
No, see, because we separate, we don't have to differentiate implicitly. Or integrate implicitly. There's no such thing. Okay. So I'm going to multiply by y and by dx. Right, because those will cancel and those will cancel. So I get y dy equals x.
negative x,
Hmm?
should be negative x.
Know what you're talking about? Yes.
Then you integrate that.
Now you can integrate because we're separated.
Y squared over 2 c equal to negative x squared over 2 plus c. And you multiply by 2, cancel it 2, leaving you y squared equals negative x squared. So you square root that.
Okay, you good to hear, Isaac Montaigne?
Sure.
It's not very reassuring. We separate, then we integrate. Putting a plus c only on one side. Now we can just solve for y because we're just looking for the general solution. General solution is just plus c.
What was the reason only adding on one side? I remember there's a reason.
Well, if I put plus c over here, they would cancel out. All I need to know is that they differ by some constant, right? So don't worry about it, putting it on both sides. All right, so multiply by 2.
Y squared equals x squared plus 2c.
You can put 2c if you are a mathematical purist.
But it doesn't matter.
It's still a constant, it doesn't matter.
That's gross.
But to be mathematically proper, we will. And then root it, right? Okay, so that will be your general solution.
Is there a 2 still squeezed in there? Oh wait, you don't have that as your hand.
Yeah. Multiply it back. So, do you want me to go through separating on the other two? Okay, this one's pretty straightforward. What are you going to get?
2y dy.
So multiply by 2y, and then move the dx over.
Can you use u sub?
That's a u substitution when you integrate it. That's what my daughter did yesterday. It was fantastic. Yeah, I just hope I don't get it. Okay. And then, how about this one here? It's best to rewrite it. How can I rewrite e to the x minus y? With our exponent rules.
It's e to the x divided by e to the y.
Okay. So,
Wait, that's not what I said though.
which is also,
Oh, okay.
so you have to get it in some form that you can manipulate, and then we can take the e to the y. And the e to the x. Okay, slow down. Right there. Okay, so that's separating variables, general solution. Okay. So that's what I had hoped you would kind of get around to yesterday, but not a big deal if you didn't get to.
Said only do the first page.
What?
Said only do the first page.
First 6 pages.
Oh.
This is pages 1 through 6.
She said first page.
No.
Could I get this handout? I was going to first.
She still has problems 1 through 6.
Pages. It says.
Well, she told us problems.
Well, that's a problem.
6 of them intact.
Okay, well, I guess that explains things. Let's see if I can find it in my mess here that she left me. No. Oh boy. Calc BC. Packets handed out, Montaigne's is in your tray. Oh, it's still there. Look at that.
What violation?
Big decimal test.
What?
I have a somewhat sick child still, so there you go.
Yeah.
All right.
Man, that's a long buzz.
Yeah. Okay. Here's a differential. They're given an initial condition. Okay, now we can actually find the value of the constant and get the function, right? So it's the same process as before, we just have a one extra step. So, you separate. Let's do this one. That's supposed to be an X. Anybody remember the antiderivative of 1 over x squared plus 1?
It's a inverse.
Yep.
Cosine inverse. Alright, that was wrong.
Cosine, cotangent, cosecant are all negative.
Oh,
So you just eliminated half of them.
sine.
It's one of the two.
I'm gonna go with 10.
You have a good tan?
No.
Or here's your sine.
Shut up. That's so bad.
I hope I'm right. Anybody care to check? I'll check. So I don't know why I don't.
Couldn't it also just be negative cosine?
Come back. Yes.
There you go. It could. But we're going to take the easy road. It's 10. All right.
Wait, is it a thing with like integrals? So like say you have the integral of cosine. Wait, hold on. That wouldn't work with like the sine cosine values, but with the inverse ones, you could have it as like either sine or negative cosine. You know what I'm talking about? If you like when you integrate it, it could be either sine or it could be negative cosine.
Yeah, it's the same thing.
Do you have to include both or no? Because
No.
negative cosine is not equal to sine.
Keep it easy. Don't make it more complicated.
But you don't have to like.
No.
Okay.
All right. Okay. We have our function, the general solution, right?
Yeah.
To find the constant, we plug the initial condition in. inverse of 0 is?
1.
What does inverse mean?
This means where is tan x equal to 0? That's a unit circle problem.
But what about the inverse part of it?
It says 0.
That's what this means.
It says 0, isn't it?
Like if tan inverse is 0,
Yeah.
that is asking where is tangent 0?
0.
Oh, I get it. Okay.
So our constant is
0.
0. And our specific solution tan inverse x.
So tangent is sine over cosine, right?
Right. Okay. And we could do a slope field and plot with that specific solution if we wanted to. I'll leave that to you for your homework.
Wait, what's the plot with that specific solution?
Well, like 0, 0, right? Like up here,
Yeah.
I gave you a specific solution of 0,
Yeah.
1. So the line has to go through that when you graph it.
Okay.
So you just do the slope field. and
So do a
connect
slope
it.
field and then draw a line through that point.
Alright.
Do I need to do another example?
I think you should do the slope field one.
Would you like me to do the slope field? Just because you don't want to do tangent slope field?
No, because they're confusing. I don't like visual tasks.
So this is only dependent upon the x value, correct?
Yeah.
Right, so we're just going to worry about the x and the derivative.
Okay. So the pattern is going to be.
So if x
directly
is
right,
0,
right?
the derivative is 1, right? Sweet.
So the patterns are going to be there.
Everything is 0, slope's 1. Okay, how about 1?
2. 1.
Try 1/2.
Oh.
It's a little shallower, right? What's going to happen at 2?
1/4.
No.
Oh,
Fifth.
fifth.
It's going to keep getting shallower, right? Okay. And then if I go to -1, same deal though.
It's undefined.
No, -1 squared is 1.
Oh,
Are we having arithmetic issues today?
Yeah.
Welcome to school. And then it's going to follow that same pattern, right? Okay. What does the graph look like through this point? So I'm just going to follow the slope fields.
Is it like a S kind of?
There you go. And that is, in fact, the tan inverse actually stops at -1. There's an asymptote. No. The asymptote is at pi over 2. Because cosine is 0 at pi over 2. You're dividing by 0 sine over cosine. So somewhere in that region. All right. Okay. Whew.
Why is that not accounted for in your slope field? Or why do you not have to account for it? Because you'd also have to do that 3 pi over 2, right?
Yeah, you would have an asymptote here, and then it would have another one, and an asymptote, another one. I don't know. This is something I didn't learn until I started teaching AP Calculus.
Nice.
Yeah. My AP Calculus course didn't include it, and we never learned it in college that I remember. So I'm pretty thin on the why of it. Let's just put it that way. Okay. All right. So that's that's all from last year. Okay, solving differentials. Euler's method. Okay, let me start back. Okay. You know how to do a linear approximation?
Yes.
Okay, so if I give you a function, a linear approximation, yeah,
Yes.
slope, you write a tangent line, right? Equation. And then you plug a value in, you estimate a value, right? Okay, that's a linear approximation. You're good, Isaac?
Yes.
He says yes half the time just to tease us.
Exactly.
Euler's method. So this can get really, so if I extended this graph and the equation and I asked for a value out here, it can get really inaccurate, correct?
Yeah.
Okay. Euler's method, what Euler's method does is takes that specific slope, but we only use it for a small distance. At that spot, we recalculate the slope and we make an adjustment and go a small distance. And then we recalculate and go a small distance. And recalculate and go a small distance. See how much more closely that can follow?
Yeah.
It's still using the equation of a tangent line, but we're only going a little ways each time before we recalculate.
Big deal is tedious.
No, actually it's not. That's the beautiful thing about it. Okay. So, to do that, what do you need? You got the point and the slope, right? And then you need the distance you're going. So let's say this is 1 and you're going to go a half a unit. So at 1.5, what's the new slope? Recalculate, boom. At 2, what's the new slope? Boom. Okay, and we put together a table that makes it pretty straightforward. Okay, so you'll usually be given the derivative in the form of a differential, and you're given an initial condition. Okay. So consider the differential xy with initial condition y0 equals 2. Use Euler's method to estimate y at 2 with a change in x of 0.5. So you can also say step size of 0.5. Or you can say using 4 steps.
So it's like with Riemann sums when they say 4
Yeah,
steps.
it's exactly the same thing. Just like a Riemann sum. So we're going to start at x is 0. And by 0.5s, 1, 2, 3, 4 steps, get to 2. Right? So here's your first part of the table. Here's the x values. And that's what's going to, like I said, that's what our small intervals are to recalculate our slope. Right? Okay, your starting y value is 2. So that's where we're at here. So you have x and y. Good. All right. Now we get to the meat of it. You need to calculate how much change there is in the y value so you can bring your line up, right? How do you do that? Well, it's right here. Okay. If you have a differential you can, remember slope is change in y over change in x, right? So we can rewrite this to give me the change in y as a function. Okay, so that is the change in the y value.
It has to be a differential.
You have to have the derivative to calculate the slope, so you can come up so many units and over so many units, right?
Yeah. Are all derivatives differential?
Yeah, it's the same thing.
Oh.
Sometimes you're just given the derivative. So we call it a differential. There are entire classes in college that you're going to go through being an engineer called differential equations, where you analyze flow rate.
Well, I was just confused because there's a y on the other side of the thing now.
Right, which is not a problem though, because we have x and we have y,
Okay.
and what's our change in our x value? 0.5. Okay, so this is our change in x. So our first problem is the x, 0, times the y, 2, times the change in the x value, 0.5, which gives us 0.
Why don't you put the change in y in, because you know the change in y still.
That is the change in y.
Oh, dude.
Okay. So now we add 2 plus 0. Right, because our y value was 2. The change in the y is 0 units. So our new y value is 2 now. Again, right, we just flatlined it. So the slope was 0. Right. Now we do the same thing again. We have an x and we have a y. Times the change in the x is the same. Right? So x, y, dx, just like we did before. So that is now 0.5. So 2 plus 0.5 is our new y value. Y'all are trying to figure this out, aren't you? Would it be easier if I did one without the numbers already there?
Yeah, for sure.
Okay. So, and you just, okay, then you just continue. 2.5 and 1. And your change in your x's gets you a new number. Add that to 2.5.
So you always have to use the previous one.
Yeah.
And then can you work it back?
It's an iterative function, basically, if you're a computer science person.
Oh.
It uses a value to calculate the new one.
Yeah.
Uses that value to calculate a new one.
Do you ever have to work backwards with this? Like, you need to
Like
work
going from
0 to -2.
You could. Your step size would be -0.5.
Oh, okay.
Right. Same method. Right. So eventually you get to an estimate of the value at 2. That would be similar to the estimate of linear approximation would give you. But it's going to be wrong. Here's the actual value.
That's way wrong.
Yeah, it's way wrong. Again, the farther you go, the less accurate it's going to be. If you're concave up, right, it's going to continue to come, it's going to be closer than the linear approximation, because the linear is just going to head out here.
Yeah.
And this one's going to try to keep up, but it never will.
I thought you said this wasn't tedious though.
Did I say that? Bummer. Okay, let me see if I can grab. is. Okay. Use Euler. Okay. Anybody want to pronounce that Euler?
Yes, yeah.
Yeah.
Don't.
It's
German.
Euler.
It's German. It's one of the very few combinations of vowels in the German language that produces an ule.
That's stupid.
No, vowels in German are ah, o, u. They're very sharp. That's one of the very few combinations that produces an inflection like ours, like A, B, C. Yeah. Okay, there's your language lesson for the day.
Very happy.
Step. Size 0.2. And 4 steps. To approximate the solution to dy dx equals y minus x squared. And y at 0 is 3.
Go 0, then 0.2.
So, you set your table up. So our x values start at 0, right?
Yes.
And 0.2,
Would you multiply the x across?
0.4, 4 steps, correct?
You don't count the initial one?
1, 2, 3, 4.
Okay.
Do you multiply the dx across?
Yeah. So somebody thinks I'm really available right now. So that will be our change in y.
So when we do these, we have to form it as dy dx, not y prime. Huh?
Yeah, and your book, which is kind of funny, I've
Switches.
never seen this before, but they call it y hat. Don't go into statistics mode, please.
Changing y.
Yeah. Well, that's exactly what it is. I mean, things do match up.
Put the average on the paper.
Okay.
Stand DB.
But, so your book will actually put that. It's just dy dx. It's just,
How many ways can you write the same damn thing?
oh, they'll put y dot. I don't know. It's a derivative. Like I said, we never really got deep into these, so I can't tell you. I never took differential equations. All right, so we have our x is 0, our y is 3 to begin with. What's our step size? It's 0.2, right? Okay, so just plug in stuff to your formula now. So 3 minus 0 squared times, what's our change in x?
0.2.
0.2. So that equals what?
0.2.
All right, so this value now is 3 plus 0.6.
Wait a second. Didn't you just break order of operation? Wouldn't it be 0 squared times 0.2?
No.
3 minus 0?
Look at the problem.
I don't get it.
When you multiply the dx over, you're
Oh,
multiplying
it has to
by
be
the whole
both.
thing.
Ah. Gross.
Everything today is gross and stupid.
I'm just stupid.
What?
I'm just stupid. We're just struggling.
No, you're not. Stupid. You might be struggling with that. Stupid. So you see where I got 3.6?
Yeah.
All right. What's my next line?
3.6 minus point, or
The x value.
0.2 squared?
Times
Uh,
0.2.
0.2 again. Yep. That one's a little bit more fun. 0.2 squared is 0.04. Right? So we get 3.56 times 0.2.
Yeah, this is already super tedious.
That's 0.82. Am I right?
I have 0.712.
What?
0.712.
Oh, it is. Yep, you're right. You're right. Okay, now add that to 3.6 plus 0.712. 4.312. And that didn't say anything again. Do you see what's going on?
Yeah.
So, what you end up with is 5.14 here, and here 6.1. Okay, so y at 0.8 is approximately 6.1. Not a hard process, you just have to work your way through it. Questions? Okay, so I'm pretty sure that I don't have it there. Finish the packet. And there's some problems at 9.3. I think I have it written on here. Actually. There you go. I apologize if some did not read correctly. Congratulations, you have now begun calculus BC.
It's so cringy though.
Now you actually have to try.
Exactly, that's the hard part.
Not that you weren't before.
I sure was.
I really like the fact that I was able to.
Here's the nice thing about BC Calc is that you pretty much know, you know derivatives and integrals. You're just applying everything we do to that. Lots of, there's new material, but you're just applying what you know to it, basically. I have a lot of memorized formulas, honestly.
Is that 14A and B or 14?
14A and B, 15 and 17.
And those are all Euler method ones?
Yes. And they put t in place of x. Not a big deal, right?
So is that English?
What?
Is that English final today, or?
You don't have any